Welcome. Um, this is our last lecture on actual 121 topics. So this lecture is going to be on a variation of linked lists that you should know about. Like the lecture on recursion, you won't need to know about doubly linked lists for the final examination. And so this is more for your information going forward. The doubly linked list, quite frankly, is a variation of lists that once you learn them, once you use them, you'll never use singly linked lists again. I can tell you I haven't written for my own code a singly linked list in probably 2.5 decades, so 25, 26 years. I always use doubly linked lists now. That's it. Now, with the final coming up, I'm going to attempt to post solutions for tests 1 and test 2. I already did the lecture, was it the last lecture? Yeah, last lecture. I've already posted the last lecture, which was going over test 3. So that had the solution for test 3 in it. And so what I want to do is go back and do test 1 and test 2, and I'll post those to Moodle. And that should help you in studying for the final examination. A reminder, the final examination is coming up on Wednesday, 10 to 12. Let me check my schedule real quick. Where is my schedule? Schedule next week. Yeah, 10 to 12 on Wednesday. So remember that, please. 10 to 12 Wednesday. What I will do with the final examination is it will be locked down to just that time period. You will have to start at 10 and you will be cut off at 12. So it will be a 2-hour test. And unlike test 3, where I gave you essentially 25 hours to do that test, this one will be just the 2-hour block at the regularly scheduled time, so 10 to 12 Wednesday. Okay, so make sure you make arrangements accordingly to be able to take the test. With that, let me drop the video and share out the PowerPoint slides for today. Slideshow, slideshow, from beginning. Okay. So last idea of the term, and just a warning, do not use this for Program 8. Program 8 is a singly linked list. This is a doubly linked list. So, so dealing with multiple links, a more useful variation of linked lists are doubly linked lists. As I said at the start of this lecture, once you learn doubly linked lists, you'll never use singly linked lists again. They're just easier to deal with, easier to manipulate, to insert and delete into. But they do require a bit more careful coding. And we're going to go over insertion into multiply linked lists or doubly linked lists today. They're also patented. This is one of those things that, you know, someone in the patent office did not do their due diligence on a patent application. And if you read the patent application and the patent that was awarded, I believe in 2003, carefully, essentially it has patented doubly linked lists, which is bullshit because I've been using doubly linked lists since the mid 1980s. So this was completely a mistake on their part. It was in common use. But a little bit of patent trivia for you where it comes to patenting code and ideas. Actually, I have intellectual property of mine that has been patented by Sandia National Labs. And so I was funded by Sandia National Labs, and they patented part of my research work. Did not include me on the patent. So there you go. So with multiple links, with doubly linked lists, each node is going to have both a forward and a backward pointer. So essentially, a singly linked list has next. So next leads you to the next, leads you to the next, leads you to the next. But we're adding a pointer called previous now, or prev, and prev will take you back to the node prior to you. So prev on the first node in the list will be null, and next on the last node in the list will be null. Okay? And quite often in these doubly linked lists, we also include a tail pointer, or what in a queue we called a back pointer. And that's because it's convenient to be able to start and run through the list in both, in either direction. Okay. So normally you just have a head pointer and a tail pointer. So you set this up basically like a queue. The head pointer is used to follow the forward links, the nexts, and the tail pointer is used to follow the backward links or the prevs. And if the list is ordered, which almost all lists are, you follow the back pointer. Why is this dropping out of the slideshow? Hello? Oh, it's because I'm using two different screens. I want to make sure this is still shared, which it looks like it is, because I had that problem with sharing. What was it, 3 lectures ago, 4 lectures ago? So anyway, back to the task at hand. So if the list is ordered, which almost always they are, then head provides a least to greatest ordering. And so you go from head through all the nexts, and you'll get from the least key value to the greatest key value. And if you take tail and follow the prevs, you'll get from greatest key value to least key value. And so this adds some versatility to the list. Okay. The struct that you would use, let me fix that typo. What the heck happened? Again, I've been getting some odd behavior with Zoom since it updated, but from current slide. From current slide. There we go. Okay. So, sorry, there was a capital S on struct, so I had to lowercase that. So the struct that you use, I'm just going to call it struct DB linked list node, so double linked list node. It includes app data or list item type or whatever you call that class that you're using for your data. And then it has 2 pointers, a next and a previous. Okay. So here's an example of doubly linked list. The nexts take you forward through the nodes, and the previouses take you backwards through the nodes. Now I've changed the way that I'm drawing these arrows. Usually I was pointing to the top because the arrow actually, the link takes you to the first memory address of the next node. But that gets really congested in these drawings. So it's easier just to draw them so that you see the nexts going forward and the previous is going back. Okay. You got a head pointer that points to the first node and a tail pointer that points to the last node. Now, the idea is pretty basic. It's two lists in one a forward list and one a backward list. They just share the same node. Insertion and removal are actually easier because you don't have to walk two pointers down the list to insert and to remove. You just need to walk one. But you still need to handle the special cases. So like inserting or deleting in an empty list, inserting before the head, inserting after the tail, deleting the head, deleting the last node in the list, inserting the first node into the list. So there's several of those special cases that we came to know with a singly linked list that you have to do with a doubly linked list. Okay. So the insertion logic, we're just going to walk through presuming that you have found the position to insert. And this is the normal insertion logic. This is not a special case logic. This is the normal case. So you find the insertion position, and I'm going to use test again, so the test pointer. And the new node, which I'm going to use a pointer called insert to allocate space into that pointer for the new node. So we're going to insert just before test. So the code is pretty simple. Insert equals new double linked list node. Test arrow previous arrow next equals insert. Insert prev equals test prev. Test prev equals insert. Insert next equals test. For 4 lines of code, that hurts. Those are some, that's not nice code. And this is where anytime you're dealing with data structures, and when you get to 201, if you're going on to 201, you must draw pictures. You cannot figure these data structures out without the pictures. It just doesn't work. I draw pictures to this day of my data structures. I published papers with a picture of the organization of the data structure in the paper because it's so hard to figure these things out just by reading the code. So the main pain here is the double indirection. And so double indirection hurts. Just a little, but it hurts. So test arrow previous arrow next equals insert. So you have to follow this. Think of the arrow as walking in the list. So it takes the node test. So test is pointing to a node in the list, and it follows its previous pointer to get the node prior to test. So test arrow previous is the address of the node, or just think of it as the node prior to test. And then arrow next is the next pointer in that prior node. And that's being set to the newly created double linked list node that we have stored in insert. So a little bit funky, a little bit confusing, but just if you draw a picture and you follow the links and you follow the arrows, it makes much more sense. So there's the picture. I've taken that same example that we used for insertion into a singly linked list, and now I've got a doubly linked list. Now the insertion, it really doesn't matter if you start at the head or you start at the tail, but it's easier for me to follow exactly how linked list insertion works, which is to start at the head. So we're going to take this list. It's a doubly linked list that has Atlanta, Dallas, and Syracuse in it. And we've got new data, which has Detroit. And Detroit's going to go in between Dallas and Syracuse. So just like that while loop we used in singly linked lists, we're going to walk the test pointer down the list, but we do not need that prev pointer because the prev pointers are built into the nodes now. Okay, So we start test right at head, and we ask that question. Is test arrow data greater than new data? Or we could ask, is new data less than test data? And if it is, you continue to run the while loop. And so test is going to bounce to test arrow next, ask the same question again. It is not, and so, or it is, and so we bounce it again. Test equals test arrow next. Now test is pointing at Syracuse, which indeed is greater than Detroit. So we have found our position to insert, okay? And here comes that code and the double indirection in the next couple of slides. So insert equals a new doubly linked list node. So insert is pointing at an empty, or at a node that has no data in it. It has garbage. We have to assume that it has garbage, even though we could set this up with a constructor. And we haven't seen that, but you can set these things up as classes, not as structs. They hurt. I'd much rather do it just as a struct. And so when we allocate a new space with a struct type, or a type based on a struct, you're going to get garbage. So that's garbage. It's empty. It's got nothing in it. It's got crap, okay? So here comes the only double indirection in the code that I've given you. Test arrow previous arrow next equals insert. So let's start prior here. I'm saying test arrow, so that's this node, previous, so that's back here, arrow next, which is this, is going to be set equal to insert, okay? And so that moves this to here. So this is now containing the address of this, okay? Next line of code, that's it for the double indirection. So the next line of code, insert arrow previous equals test arrow previous. So again, test arrow previous is the address of the prior node. And we set insert previous to be that. So insert arrow previous equals test arrow previous. Sorry, I clicked when I shouldn't have. Okay, so we copied that over. So if you look, we already have the next pointing in the right spot, its previous pointing in the right spot. We need this previous to point to here, and this next to point to here. So we need this previous to point here, and we need this next to point here, okay? So next one, test arrow previous equals insert. So test arrow previous equals insert. So that copies the address here. And then the last pointer we need to fix up is insert arrow next. So insert arrow next equals test. That copies the address out of here and puts it in here, pointing up here. Now this is a lot of pointers going seemingly all over the place. But if you follow the nexts, head takes you to the first node, next takes you to the second node, next takes you to the third node, next takes you to the fourth node. Tail takes you to the last node, previous takes you to the previous node, previous takes you to here, and previous takes you to here. So those work. I'm going to redraw this, so I'm just going to clean this up a little bit. So that makes a little bit less of a mess. So from here, I'm just going to slide this node up into here and slide these nodes over to make the drawing a little cleaner. And then all we have to do is copy over that data. Detroit 762, and it's copied in, okay? That's a doubly linked list. or at least insertion into a doubly linked list. Deletion works much the same way. You're going to slide test down the list until you find the node that you want to delete. So I am going to stop the share here. Okay. And now, what I would like to do, actually, I'm going to escape out of this. I'm going to open a Notepad++, close that, close that, close that. Okay. I'm having trouble getting the screen I want. Notepad++. Where did Notepad++ go? Ah, here we go. Okay. So now I'm going to just write some notes about deletion. Okay. So we need to find the node to delete, or to remove, I guess I should say. So I'm just writing some notes here, and we'll probably reorder these because sequence in these doubly linked lists is incredibly important. So if there's only one node in the list, okay. I'm going to put one up in here. So we should throw an error if the list is empty. Okay. Pluralize that. Okay. Otherwise, we have a normal case. Okay. Okay. So we throw an error. Otherwise, we find the node to remove. Actually, now that I'm thinking about sequence, I want to handle this one first. If you think about it, we are deleting both the head and the tail. The first if statement is the head or the tail. And so we need to move that up to there. So if there's only one node in the list, that is head equals tail equals test, then we need to handle that. And in fact, there's a case just before this, if we didn't find it. Okay. So I think that's a good order right now. So if the list is empty, it's going to be an error. We need to then search for the node to remove. And if we don't find it, we're going to throw an error. Else, if there's only one node in the list, we need to handle that special case. Else, and this probably should be split into two cases because the code is going to be different. Else, if the node is head, handle this special case. Else, if the node is tail, handle this special case. Else we have a normal case. Okay. Now I'm not going to be concerned about how we figure these things out. What I'm concerned about is the code that goes in here. And so I'm going to indent over. If there's only one node in the list, okay, we're going to use something I call temp data equals test arrow data, delete test, set head and tail to null, and return temp data. Okay. Now, usually we don't return the thing that we delete in linked lists, but I've written it so that it does. So depending on your application, you may or may not do this part and this part, but you definitely have to do these two. Okay. Else, if the node is head, handle this special case. Okay. So head equals head, arrow next, temp data equals test arrow data, delete test, return temp data. Okay. Now, what I would like you to do is just pause the video right now and come up with your own code for handling the tail. And so pause it right now, write down the code that you think is going to be used to delete the tail or to remove the tail, and then unpause the video and see if you got it right. Okay, so here we go. If the node is tail, handle the special case. So test is pointing at tail. That means that we can say tail equals tail arrow previous. Okay. Tail arrow next equals null. I just realized that I was not careful enough up in this case. So head equals head arrow next. Head arrow previous equals null. So I missed handling that one pointer. Like I said, handling these pointers is difficult. There's a fair amount of housekeeping here. So back down to the one that I just had you do. So you probably missed nulling out the pointer, which I did right here. So tail equals tail arrow prev. Tail arrow next is equal to null. Temp data equals test arrow data. Delete test. Return. Okay. So that should be our code for that case. And now we have the normal case, and the normal case is a fair amount of messing around with pointers. So test is what we need to delete. That means that test arrow next, the node that follows it, has to have its previous pointer altered. Test arrow previous, the node prior to the one we want to delete, has to have its next altered. Okay? So, if we think about this, we have two pointers that have to be altered. That is test arrow previous arrow next has to be equal to something, and test arrow next arrow previous has to be equal to something. Okay, so test arrow previous arrow next, the node before test, its next has to be set to the node after test. That would be that. Test arrow next, arrow previous, so the previous pointer in the node after test has to be set to the node prior to test. Well, the node prior to test is that. Now we copy out the data. We delete test, and we return temp data. And that's it. So the special cases aren't that bad. I did forget to null out the previous here. Did not forget to null out the next here. Okay. If you really want to understand what's going on, you're going to have to draw pictures. Okay. I can show you lab books of mine that I keep my notes in that have little pictures of data structures drawn in them, exactly like I've shown you in the PowerPoint slides. Okay. You just need to draw pictures. That's going to help. So the really ugly part of this is right here. And I could simplify this if I used a couple of temporary pointers or pointers to help me. It might clean this up a little bit. It'd eliminate these double indirections. Okay. But the double indirections are just a matter of following those pictures carefully. Okay. And those are doubly linked lists, at least insertion and deletion into doubly linked lists. Now, there's a variety of linked lists and doubly linked lists that we call rings. And they're very useful in computer graphics and in, well, the main use is in computer graphics or computer vision. Think of a polygon. The last vertex in the polygon has to point back to the first vertex in the polygon. Okay, so I'm going to drop this share, and I'm going to share out a whiteboard. Okay, so if you have a node here, that's a vertex, and maybe that's vertex 1. And you go over here, not really a straight line, but vertex 2. Then you go down here, that's vertex 3. You go over here, that's vertex 4. I like concave polygons, so that's vertex 5. And then back to here. So you can see the thing that comes after 5 is 1. The thing that comes before 1 is 5. Okay? So if I were to do this in a linked list, I would need 1 to go to 2, to go to 3, to go to 4, to go to 5, and 5 should come back to 1. If this were a doubly linked list, it would have pointers pointing back. And it would have a pointer that goes like that. Okay? So these are called rings. And rings are fairly useful when you're trying to represent things like polygons. And we do this all the time in computer graphics, and we do it all the time in certain parts of computer vision. And my field of study, my field of research is computer vision. So just yet another idea. These are ideas that I'm not going to test you on. I am not going to ask questions on the final examination on these things. But these are ideas that you will hit out in the real world, out in industry, in graduate school, and you'll have to know that they exist, and you'll have to have at least a passing familiarity with them. And so that's why I'm introducing you to these concepts at this point. With that said, that's about all I wanted to cover today. So let's see, I'm going to get rid of that and get rid of my PowerPoint slides. Turn back on video. So we're back to video. And so again, a little bit short lecture today, following that long lecture from last week, or to end last week. So far I'm having a little better week, but I'm still behind in my work, as we all are. This is the last week of this term, finals week next week, and then we are done. The end of this term could not come soon enough. In some ways, it's flown by. It seems like just a few days ago that we found out we were going to have to go online. And in some ways, it seems like it was an eternity ago that we've been slogging through this forever. For those of you who stuck it out, for those of you who have watched the videos, for those of you who have kept up with your programming assignments, my hat is off to you. This was not easy. And you staying engaged and you continuing to keep up with the class is a credit to your resilience and a credit to your character. We are better than we let ourselves or we allow ourselves to believe. You are better than you allow yourself to believe. Stick it out, push through, do well on your finals, and you have finished a term that for the rest of your life you will look back on and say, I did that. I came through that. I survived that. That is something you should be proud of. And it is something that I am proud of you for. That is sticking this out, staying engaged, finishing this stuff off. So with that, the next two lectures, Wednesday's lecture and Thursday's lecture, are going to be essentially overviews. I might go back and look at test 2 because we never had a review of test 2. And so I'll probably do a review of test 2 for Wednesday's lecture and then a review for the final examination on Thursday's lecture. So take care, stay safe, stay healthy, um, you know, stay away from people. So bye-bye.